Here we go. So we're going to talk about something called circulation density today. Circulation density. So before we do that, let's talk about orienting a boundary to a surface. So we talked about orienting a path, right? And we've talked about orienting a surface. So what about when you have a surface that has a boundary, and we want to orient those together? So given an open surface S with a boundary C, you look at an n vector very close to C, right? An n vector on S that's very close to C. And then with the right-hand rule, for n will indicate the positive orientation of C. So a picture is definitely needed here. So I've got this oriented surface, and we're going to decide what's the orientation of S. Is it upward or downward? So if upward, like I'm showing here, then you look at an n vector close to C, and you use the right-hand rule for the direction of n. And so then would that be taking me counterclockwise or clockwise around in this little loop around n? Counterclockwise, right? So like this. Try that again. It's supposed to be an arrow. There, that was better. All right, so so if you choose upward orientation for the surface, that means the ends point up, and then with the right-hand rule then would be a little counterclockwise loop. And then as you go by here, heading kind of left to right, you see that? That will determine, then that says, oh, then that's the direction of C. C will go in the same direction as N as you sweep around close to the boundary there. Does that make sense? And then same thing back here. So if N points up, we're talking about counterclockwise. And then what would that mean? As it gets close to the back boundary there, it would be what? Right to left. And that would indicate then that the direction is this way, which is consistent with what we've already done, right? So that's consistent with this. So we're aligning the orientation of the surface to the boundary. All right, another one. So I've got two. So I'm doing outward. So this S is just it's a hollow shell, right? There's an open top and an open bottom. So this is a surface. And so we're orienting, the orientation is outward. And so with outward orientation, looking at this little one here, I'm going to go clockwise or counterclockwise according to the right-hand rule? Counterclockwise. So what would that mean for this top part of C? Clockwise or counterclockwise? Right, so as we pass by this way, we're going to go the same way on C. And that ends up being clockwise up here. Does that make sense? And then the bottom, so outward orientation is going to be counterclockwise. This. So then on the bottom here, looking at this, is it going to be left to right or right to left? This way. So it depends how you're looking at it. If you're looking at it from the top, if you're looking at it looking down, then it's counterclockwise. If you're looking at it this way, then it's clockwise. But in any case, it's going to be that way. Okay, now this is consistent with what we said about the walking thing, right? So if you're walking on the boundary such that your head is pointing in the direction of N, then the surface would be on your left. So if you're walking on the boundary, you could either walk this way, like up like this, or like you're walking this way. So you want to have from toes to head pointing like a vector this way up, and then the surface would be on your left, and that would determine the orientation of C. So that should work on these two as well. If, let's see, so how would you walk on this so that the surface is on your left? You'd have to walk this way, right? No, raise it up. Isn't it? Yeah. Yeah. So you'd have to walk this way. No, wait, so no, but you'd be out like this. You'd be sideways. Sorry. So you're coming out at you. So you either walk this way or this way, but to have the surface on your left, you'd walk this way, just like we said before. No, you're gonna walk so that your head points in the direction of N. Right? So you're gonna walk so that your body and your head is pointing in the direction of the N vector, which would be out. So you'd be walking like this, on the edge, but on the outside. Right? And so then to have the surface on your left, you'd have to go around this way. Does that make sense? Okay, so then just recall that we said the circulation around C was given by the line integral, right? F dot dr. Remember line integrals? So then what is circulation density? Circulation density is the strength of the circulation of a vector field in a chosen direction, say V. So we use this notation for that. Circulation density, sub V, so that's the direction of the vector field F. Okay, and so how do we calculate that? So it would be the magnitude of, so the circulation around C divided by the area inside C. And then you would let that little boundary C and the area inside C go to 0. So what does this mean? It means that if the smaller your area combined with the larger amount of circulation would result in higher strength of circulation, right? Circulation density would be higher. Right? So if you imagine a large area and a low value of circulation, right? You imagine there's not very much strength of circulation there, right? But you get a very high value of the line integral of circulation for a low area. Then you have really strong circulation force, right? Does that make sense? And so then that limit of that ratio, as you make that loop small, would be the value of circulation density. Okay, so this should kind of feel like something else we've talked about. We'll get to it in a second. Okay, so here's how we would calculate that. So the limit of the line integral divided by the area inside the loop, and then we're going to let that whole thing get really small. And so that the limiting value of that is how strong the circulation is. So circulation density. So it has units of, what does this have units of? So it could be like joules per meter squared, right? Because it could be like, you think of that as work if it's a force field. It would be work around the loop per area, right? So per unit squared. So circulation density, does it feel like a familiar idea? Some are nodding. What is it like? Strength of, so it actually becomes like a point, right? So it's kind of like strength of circulation at a point. Not flux, because flux is like how much flow we get through a surface. That's something different. Strength of circulation, point-wise strength of circulation. Curl, right? Curl. All right, so when we choose V to be N for a surface, right? So now, so we have a surface S, and choose the direction that we want as N for a surface. Then our circulation density becomes the curl of F dot N. So it's, what is it? It's the magnitude of the curl in as much as in the direction of N, right? So that's our dot product, right? So it's like we're taking like a portion of the curl, right? We're taking whatever portion of the curl is in the direction of N. So then that's the strength of rotation for that particular direction N. So we have kind of two different definitions, two mathematical definitions for circulation, right? We have this one, circulation density. We have take the line integral and then divide by the area within it and let that limit, take the limit as the area gets small. Okay, then we have this one. Curl is essentially circulation density. Curl is essentially the magnitude. Sorry, the magnitude of curl is essentially circulation density, the strength of rotation of the vector field at a point. So if we take the part of that strength, that magnitude, in the direction of N for some surface, then we have circulation density for that surface. So these are two different. But they're the same. I mean, so they're the same, but they're kind of in a different, expressed differently. They're both circulation density. And again, it'd be like, you know, joules per meter squared or something like that. Joules per whatever squared would be your units for circulation density. Work per area. Work per area. But rotational work, right? So rotational work per area. It gives strength of rotation. Okay, questions before the next slide? Last chance. Okay. So like we said, so this is the same thing I wrote at the bottom of the last slide, that the circulation density is what? In the direction of N for a surface. It's the magnitude of the curl in as much as it's in the direction of N. That's why it's dot product. So we're just taking the magnitude of strength of rotation. We know curl is a vector, right? Curl is a vector function. We take the magnitude of that in the direction of N, so that's going to be some portion of the curl, and that's the circulation density in the direction N. And we said there was two ways to compute it. Okay, so let's take a look at this. So suppose this blue vector field is the curl of F. I think they got a new light bulb. Colors are showing up much better. Better late than never. Okay, so it's like we're taking, so here's this blue vector field is the curl of F. And we're going to take, when we do the dot product, we're going to take the component of that in the direction of the normal, which I'm showing as N. So if the curl is, say, this way, can you imagine the orientation of the rotation? What's the orientation of the rotation if the curl is like this? How is it spinning? Right? Coming a little bit out at us and to the right, right? So the spinning is this way, right? Or the turning is this way. So I don't know if we can draw this. Try. Not bad. So does that make sense? Because the curl is, the direction of the curl is showing you orthogonal to the plane of rotation. So then we're taking, so when we do the circulation density in the direction of n, we're taking just the portion of that in the direction of the red. So we're going to lose a lot of that. So the curl is like the full strength of the rotation in that direction. By taking just the portion in the red direction, we're going to lose a lot of that strength, right? So it's going to be, the circulation density in the direction of n is going to be a lot less than the curl at that point, for this particular, at this point, right? Because they're not very much in the same direction, right? They're like almost, I mean, maybe it's like 70 or 80 degrees different, right? But then it's a point-wise phenomenon, right? So as you move around, so now maybe we get almost all of the curl for this one, right? And then that curl is more like flatter, right? So the curl gives us another way of calculating circulation density. We saw that before. Okay, so we want to look at one element of S with a boundary C. So let's see if I can draw that here. So suppose we break this up into elements. Okay. I'm going to isolate one element right here like this, right here. So that one right there. And I'm going to call the boundary delta C, because this is a little element, so delta C is the boundary around that thing. And then the area is delta S. So the circulation for that little element, the circulation density in the direction n. So we saw this before, right? So it's going to be the line integral around our loop of that element divided by the area as the area gets small, right? So we saw that before. And so since we're letting things get small, that's going to be approximately, you imagine this like shrinking to a point, right? So it's like shrinking, so circulation density is a point-wise phenomenon. So we imagine that whole thing shrink to a point. So then our delta C boundary becomes like an infinitesimal loop around that point with an infinitesimal area, ds. So it's like we're evaluating the limit, right? So I'm taking the limit here and letting everything get real small. So if this is the case, then I can write what the line integral is. Just multiply, if I just multiply the circulation density by ds, that's what the line integral is. Okay, so that's what I'm doing there. I'm saying that the line integral, the numerator here on the right, is the circulation density times ds. So that's just algebra. But then we said that the circulation density could also be written as curl of f dot n, right? That was the other way we wrote circulation density. Okay, so now we want to sum up. We want to sum up all the circulation around each DC. So imagine doing that process for every single one, right? So do it at every point on here. Partition this up into lots of little elements, and then as those elements get small, we have more and more elements, and then we're going to sum up. We're going to sum all these up, right? We're going to sum all these up for the whole surface. So that there's really two ways we can take that, right? So there's two ways we can go with that. The first way is we can sum up this. Summing up all these would be summing up all these. The circulation density times a little bit of area is circulation, right? Because circulation density is circulation per area. So if we take circulation density times the area, we're going to get circulation. We'll sum all those up. So that's one way we can go with that. The other way we can go with that, we've seen before. When we sum up all those circulations of all those points, we end up getting the circulation around the outside boundary of it. So if the outside boundary of this is C, when we sum up all the circulation integrals as things get small, it turns out to be just the circulation around the whole outside, the boundary of the surface. Remember how that happens? Remember that principle? Right. So if we add up all, so like add up all the circulation for every element, what happens to all the interior? So we're going to break each one of those up into 4 pieces, right? Those paths are 4 pieces each. And all the shared boundaries, what happens to those? They cancel because we go this way on this boundary, but then when we're on this element, we go this way. So those, when you add those two together, they cancel out. So all the shared boundaries cancel out, leaving just the ones that aren't shared, which is they all sum up to the outer boundary, C. Okay, so that means since these are both equal to the sum of all the circulation integrals in C, either we think about it as they all cancel out in the middle and we get just the boundary, or we think about summing up all the components of the curl in the direction of n. Both of those are the sum of all the circulation, all the points. So those two are equal. And then when things get small, this becomes the surface integral of the curl. So if you're summing up over all these little areas, that's going to be a double integral of this over the surface of the curl. And so since they're both the sum of the circulation around each little DC, they themselves are equal. So again, 2 ways to compute the circulation. Either just the circulation around the outer boundary of the surface, or the surface integral of the curl, which is what? Summing up all the little amounts of circulation as calculated by circulation density times area. And so we're good at these now, right? We learned these a couple weeks ago, and now we're good at these. It's just that the vector field that we'll be doing the surface integral, the flux integral for, is now the curl of F. And what was that? That was one type of what? Rate of change of F. Rotational rate of change, right? The curl was rotational rate of change. And now we see that rotational rate of change is circulation density. Strength of rotation pointwise. So look, summing up a bunch of changes calculated by rate of change times little change in independent equals to the total change on the boundary. We've seen that before. What's that the general idea of? So summing up bits of accumulation calculated by rate of change times change in independent is equivalent to the overall change at the boundary. What is that talking about? What is that? No, that's the fundamental theorem of calculus. If you were thinking that and you were shy, shame on you. Fundamental theorem of calculus. Summing up lots of little changes, in this case, changes, little circulation changes, each computed by rate of change times change in independent, is equivalent to the total change at the boundary. Total change at the boundary. So this is another fundamental theorem of calculus. This in particular for open surfaces with a boundary C, right? Okay, questions on this slide? Okay, so this is what Stokes' theorem is. So given an orientable open surface S with boundary C, whose orientation is determined by N as defined for S, then the circulation around the boundary is the same as the sum of all the circulation, little circulation on the inside. Now, in terms of using it, calculating stuff, you know everything. You've already done all this. You've done line integrals, right? You've done surface integrals, or flux, right? The only difference is the vector field that you're doing the surface integral for is now the curl of whatever this vector field is, right? And this makes sense, right? Because we said that's rate of change, right? So that curl is one type of rate of change of F. Rotational rate of change, right? Rotational rate of change. Okay, so I'm just going to give you an example and put you to work. So we're going to verify Stokes' theorem. So what does it mean to verify a theorem? Remember we talked about this before. What does it mean to verify a theorem? Right. So if you're verifying a theorem, that means you're gonna calculate both sides separately, show that they're equal. Okay, so all right, so the vector field, let's get rid of that. So vector field F is y squared x z squared. And S is the part of z equals x squared plus y squared below z equals 1, oriented upward. Okay, again, verify means you're going to do them both. You're going to do this line integral, and you're going to do this flux surface integral, and show that they're the same. So you're either making progress, or you're getting... You don't have to whisper. All right, is there one side that you want me to do? Line integral side or surface integral side? So was there a mixture there? I think more people want the line integral. So the line integral, what is C? We're just taking the part of the paraboloid below z equals 1. How is that an open surface with a boundary, right? So what's the boundary? Is it this thing right here? No. Right, so remember, an open surface has two sides. If it's an orientable open surface, it has two sides. And then the boundary is like what you'd have to cross to get from, if you're walking, to get from one side to the other. So what is the boundary? The rim up here, right? So there's the outside of this, that I can see most of it. And then there's like the inside of the bowl. The boundary is what you have to cross to get it. So that's what we're doing the line integral around that blue circle C. So how do we do line integral? First we have to parameterize the surface, or parameterize the curve, right? Now we get one variable when we do curves. We get two variables when we have surfaces. So how am I going to parameterize this thing? I got one variable and three coordinates, x, y, and z, to write that path. Anything that we know right off the bat? But any of these components that we know right off the bat? Z is always 1, right? Z is always 1 for all the points on this curve. So now we got to get all the x and y coordinates of those points on that circle in one parameter. What will our parameter be? So t, but t will represent angle measure, right? We're going to do angle measure because it's around a circle. So I'll use t, that's fine. And then So our x coordinate will be, because it's radius 1, it's just be 1 cosine t and then 1 sine t. Okay, we're off to a good start here. And then we need, for the integral, we need dr. So dr is negative sine t, cosine t, 0. We've got f. What's f? I gave it to you. Y squared x z squared. So y squared is sine squared t. Remember, we rewrite the vector field in terms of our parameterization of the curve. So sine squared, cosine, and 1 squared. Now write this up, the integral. So we're going to integrate, and it's going to be f dot dr. So we're going to get negative sine cubed plus cosine squared and that t from what to what? 0 to once around the circle, right? So we could spend 5 minutes doing that, or we could put it in, use technology at this point. This isn't about integration techniques. So if you set, did anyone get that far by yourself? Handful, okay. Doesn't make sense. So this is blast from the past here. Don't forget your line integrals. Any questions on setting up that line integral? All right, so let's evaluate it, and then we'll see and then what did we get for the surface integral of the curl? Anyone get an answer? Here? Nope. Where am I? Where's Keynote? Here? Yes. Okay. So let's put this in. So in Control-Shift-I, 0 to 2 pi. Negative sine x. Another set of parentheses here. Plus cosine squared. Looks like it's pi. So it's pi. So we need so the flux of the curl for that surface for the paraboloid should be pi as well. Did anybody get pi for that? One person, 2 people. Should we do it? You can't do it with Green's theorem because it's similar. So actually, Stokes' theorem is Green's theorem in 3 dimensions, right? So because if you have something in the curl is, remember the curl is qx minus py, right? The z component of the curl is qx minus py. So if you're in the xy plane only, if everything is in the xy plane, then your curl just reduces to qx minus py, and you're doing Green's theorem. So Green's theorem is a special case of Stokes' theorem in the xy plane. So yeah, if it felt like Green's theorem, then that's correct. So let's do. So what is the curl of f? I'm just gonna write it down. I won't do it. I'll trust you guys. Curl of f is nice and loud.
I got 0, 0, and 1 minus 2y.
0, 0, 1 minus 2y. People are nodding. Did I write it down right? So So when you do the curl, you should get that. Okay, our parameterization of this for the surface. What are we going to do it in terms of? We could do r and theta. We could also do x and y, and maybe end up switching it to r and theta later. So we'll just go ahead and do r and theta, and we get r cosine theta, r sine theta, and right. So we mean z to be is this squared plus this squared, right? Z is x squared plus y squared on that surface. So when you do this squared plus this squared, you get r squared. That's right. So then we have to do r cross r theta. Anybody have that? Negative 2r squared cosine theta?
Yes.
Negative 2r squared sine theta?
Yes.
And? R. So, remember, so we saw this in recitation last week. When you do r cross r theta, so we're going to look at this now and make sure, so this is, what is this? This is our field of n vectors, right? When you do that cross product, you're establishing the orientation of all the n vectors for the surface as r and theta change. And with upward orientation, what does that mean? Upward orientation would mean, what about one or more of these components? Z should be positive for these n vectors, right? Upward orientation of the surface means the n vectors need to have a positive z component. So, did we get it on the first try, or do we have to switch it? We got it, because r is positive, and so z is positive, so this is the right one. If this turned out to be like negative r, then this cross product would be for downward orientation, if that z were negative. But since it's positive, we're good. We use this one. Okay, so we got it. So we're going to do curl of f. We're going to do this dot this one. And when we do that, and so this will be 1 minus 2 r sine theta, is that right? So as we do curl f dot, so we do the dot product of these, right? Okay, and then these are going to just, the first two components just go away, right? 0 and 0 just go away. So really the dot product just becomes the product of the z's. 1 minus 2y is 1 minus 2 r sine theta times r. And now we're doing the integral, and r goes from 0 to 1, theta, 0 to 2 pi. Because this thing flattens into the disk, right? This thing flattens into the unit disk. So we're just we let r vary from 0 to 1 and theta vary from 0 to 2 pi. Now, the question is, do we do r dr d theta or just dr d theta? Because we chose our parameters to be r and theta, we don't do r dr d theta. We're not converting from rectangular into polar. We started in polar. And when you start in polar, you're going to just follow the general formula for u and v. And in fact, this is the r, right? So this is that r. When you did the cross product, this is that r that would be like r dr d theta. It's already there. Okay, so let's put that one in. No, let's just do just do it. That's easy. So we're going to get r squared over 2 minus 2r cubed over 3 sine theta. Check my math. And then from 0 to 1, d theta. Please let this be pi. Is this pi? Okay, good. So then I'm going to plug in 1 and 0, and I'm going to get just 1/2 minus 2/3 sine theta. So 0 to 2 pi of 1/2 minus 2/3 sine theta. D theta. And what's that? 1/2 theta minus plus 2/3 cosine theta. And so, yes, we get pi. Because you put 2 pi and 0 in here, those go away, and you get pi. Check. Verified. Okay, questions on this example? If you have a question, don't hesitate to ask. Yes, please. You can't do it. So Stoke's theorem works only for an open, orientable surface. If it's closed, that's Thursday. Other questions? Okay, another example. Can I erase? So here I want to find if f equals z squared 2xy 4y squared and c is the counterclockwise triangular path shown. We're going to go from 1, 2, 0 to 0, 0, 2 to 2, 0, 1 so 1, 2, 0 to 0, 0, 2 to 2, 0, 1 and back counterclockwise. Oh, I forgot to say something important about that last example. Put this on hold for a sec. So what do? We said that this, the surface integral of that paraboloid below z equals 1 is the same as the loop integral, the circulation around C, right? So let's forget about the paraboloid for a second and just look at that loop around C. What would be another way to compute then this? So forget about the paraboloid. Say I just said find the integral, the circulation around C, which is the unit circle at z equals 1. It's not circumference because it depends on the vector, right? It has to do with the vector field because we're going through this vector field. So now you have two ways to do that. You have two ways to find that, not just directly doing that. But what would be another way to do that? No, hint. It has to do with Stoke's theorem, not geometry. You're all thinking geometry. So pretend that we never had that paraboloid, okay? I just said find this circulation integral. Okay. In that case, you have to convert from rectangular to cylindrical, unlike when we did it before. Then that would be R. But what is S? What's your surface? You have a surface. No, C is a path. S is a surface. So how can we use Stokes? Yeah. Not along the curve, right? The curl is for a surface, right? So Stokes' theorem says that it's a surface integral, right? A surface integral, meaning some surface. Which disk? That's right. Right. So the unit disk at Z equals 1, right? So if you made the unit disk at, so let's call this S star, the unit disk at Z equals 1, what would be the surface integral over S star of the curl of F? We already know what that is. What should it be by Stokes' theorem? Pi. Right? Because, let's forget about the paraboloid. We have an open surface, this unit disk up here at Z equals 1, with a boundary. And we know that that circulation around that boundary, we've already calculated it as pi. So that would mean that the surface integral of the curl for that unit disk would be pi as well. So what we kind of have here is what's called, so you remember path independence? Path independence means if you were in a conservative vector field and you took the line integral from one point to another, it doesn't matter what path you take, right? It was just the difference of the starting and ending points. So what kind of independence do we have here? So our starting and ending point now is like a boundary. As long as you have the same boundary, it doesn't matter what surface you have. So with Stokes' theorem, you have something called surface independence. Any surface, any open surface that has C as its boundary, is going to give you the same flux of the curl integral. Right? Because they're all equal to the circulation around that boundary. So if it's, as long as it's any surface that has that. So we could have, what's another one? What's another surface that would have this flux integral of pi? Can you imagine another one?
Like a lower hemisphere?
Yeah, so if we did a sphere, right? A hemisphere? Either way. So you could do the top half of the sphere or the bottom half of the sphere. A cone, right? A cone that has C as its boundary. So any open surface that has C as its boundary in this is going to have a surface integral of the curl of F of pi. So that's the idea of surface independence. Okay, now back to this one. I've made a mess that I can't erase, so let's try this. I can do that. So let's just talk through how are we going to solve this triangular. So I want to do the line integral around this triangular path. So if I did that directly, what would that consist of? What would I need to do? to directly do that. 3 lines, 3 integrals. I have to parameterize this 3D line and do its line integral. I have to parameterize that and do its line integral and that and its line integral and add them all up, right? Alternative. You have another way now. Right, exactly. So we're going to do Stoke's theorem, and we're going to do the surface integral of what? So what vector field are we going to do the surface integral of? We do this one, surface integral of this? Curl of this, right? So we're going to instead do the blue plane as our S. And we're going to do the surface integral over S of the curl of F dot ds. And because it's a plane, all we need to do is find the normal vector, and we don't have to do the cross product, right? So remember that? So if you have a plane, so we would just need to find it's a constant normal vector for a plane, right? So I just need to find that normal vector, and I could just do curl of f dot n, and then how would I finish the integral? So I can rewrite this as, and how would I find the normal vector? I'm going to find the vector on 2 sides, a vector there, and then do the cross product, right? Will give me, so I end up having to do a cross product, but that will give me n, so we do dot n. And then it's going to be, what? ds. So what then variables how will I project this and finish it? So then we're just going to have a double integral, right? So we need variables for the double integral. So we're going to project, the easiest thing to do is project into xy, right? And so you have dx, dy, dx, or dx, dy. So projecting into the xy just means taking these triangles and taking the z coordinate off, right? Just take the z component off. Just flatten that thing in the xy plane. And you get something like this. 1, 2. Unit vector. Thank you. Yeah, thanks for clarifying that. So our projection will look like that in the xy plane. And then you got a double integral to do. Double integral of whatever your dot product is over that region. You got 2 choices, right? Type 1 and type 2. What are you going to choose? You do dy dx or dx dy? Dx dy allows you just to do it in one integral, right? So, do I have an answer here? So I'll leave you to practice that one. So it wouldn't be a bad idea to verify that, but if it just asks you to find that line integral, all you'd have to do is the surface integral of the curl. And then you're using Stoke's theorem. You say by Stoke's theorem, it's equal to what we wanted.